Uh, Mit?
Yeah, Kiran.
Yeah, I started that session. Once he comes now, we can start the session. Okay.
Yeah, it's live on YouTube now.
Yeah, yeah. Once he comes now, we can start. I think she joined.
Hello, I'm back.
So should we wait for some more time for people to join the YouTube live? Do you have a count of how many are in here?
Ashwati, it is live.
Yes.
You can start.
Okay.
Yeah.
Good morning, good evening, and welcome to Incoy's Popular Science Talk. Today we have with us Dr. Danielle Su. She is a physical oceanographer based in Singapore. Currently, she is working with the Singapore government on designing scenarios for coastal protection and climate change adaptation. Her PhD at the University of Western Australia investigated flow topography interactions and their variability across seasonal and interannual scales in the Northern Indian Ocean and was under UNESCO's second International Indian Ocean Expedition. Postdoctoral research at CNRS Paris examined the physical mechanisms for carbon storage across regional ocean basins. Her research involves the development of regional models to investigate sub-mesoscale processes and their contribution to air-sea fluxes and biological productivity. Today, she has joined us for a special talk. This is our second international talk in our Popular Science Talk series, and she'll be sharing with us about the challenges in regional ocean modeling, the island issue. Over to you, Dr. Danielle Su. You're on mute.
Hello, thanks very much, Aswati. Sorry for that. Thank you very much for the introduction, and thank you very much to the organizing committee for inviting me. It's really a privilege to be able to give a talk for celebrate INCOI's 25th anniversary. Um, Previously, as part of the International Indian Ocean Expedition, it was really lovely to work with a lot of you. I think Hiran was just saying to me that we actually worked together during the IIOE too, and of course, Nimit is a very dear friend and colleague of mine. So without further ado, I'll start on my talk for this evening. So right now, I'll be talking on the challenges in regional ocean modeling, the island issue. So first of all, let me get this going. Let me share my screen. Okay, so hopefully everyone can see my screen. If it is, all right. So as I mentioned earlier, I'll be talking on the challenges in regional ocean modeling and with a focus on how this applies to the challenges in modeling islands. So to get started, we have to address like what is our definition of islands in this context. And in this case, we often associate islands with land masses with the characteristics of smallness, the isolation, and basically land boundedness. All right, and there are implications for it in the sense that when we apply climate impact assessment methods, it simply cannot be easily downscaled for island application. Right. So a brief overview of what I will cover today is a background of the importance of islands, the databases on where we are at in terms of knowledge for observations in locations where islands are concentrated, and then following about modeling for scale, which is about how do islands, when we look at climate data on a broader basis, right, what are the challenges that we see when it's being applied for islands, and of course, future directions that we can take to try to resolve these challenges. So in this image over here, we can see that there are some very, these are satellite images. So this is from a meteorological So for meteorology, islands do play a very fascinating role in altering weather patterns and creating localized climate conditions. Their topography, their interaction with atmospheric and oceanic conditions, right, and their small scale geographical features, it can give rise to very unique microclimates and meteorological phenomena that can vary significantly from one island to another. So one of the most significant ways that islands can alter weather is actually through their topography. So the elevation, the shape, the orientation of an island can influence, the movement of air masses and how precipitation develops over the land mass. So this over here is one of my very favorite pictures. So this is from the Sentinel satellite imagery. We can see some very beautiful von Karman vortices, right? Some eddy shedding based on, in the atmosphere. And similarly, we can see that for like the Canary Islands, all right? So we can see just by the presence of an island being there, it has a significant impact on the weather conditions that develop around it. Some of the things that can also islands can do is, for example, for orographic lift, like islands with very mountainous terrain, can force air masses to rise, and when they interact with the mountain range, right, it can create a different climate conditions on either side of the mountain ranges. The complex topography of the islands can also generate very localized wind patterns, as we can see here, and they are also responsible for example in the archipelago of Hawaii. We can see that there's this effect called wind shadowing, which is the interaction of the wind shadowing on the either side of the islands and the proximity of them to each other. So from an oceanic point of view, so these are also from remote sensing. So these are some satellite images of chlorophyll plumes, all right? And we can also see here that there's also these like beautiful eddies and, some beautiful vortex shedding happening in the lee of the islands as well. So we have like, for example, here in the Gulf of Finland, the Bay of Fundy, all right, in Australia, and even in lakes as well, we can see this in Canada. So, for example, in the context for islands, they are typically surrounded by oceans, and just with the interaction of the flow topography interaction of the island and the currents around it, it can generate a significant impact on the surrounding ecosystem. So, for example, we can also see that later I'll talk a little bit more about this in terms of the island mass effect, where we actually find that islands are hotspots of biological productivity, right? And we can also see this happening around atolls and seamounts as well. Okay, so islands also have something what we can call their own unique microclimates because of their small size and their unique geographical features. And this applies to not just above land, but also within the sea as well. Yeah. Sorry, excuse me. So this is what I mentioned earlier about the island mass effect. The island mass effect is essentially a phenomena where we have these biological hotspots of productivity, and they've been likened to being called an oasis in the blue desert. Right? Is that you can find in a rather oligotrophic, in a rather nutrient poor ocean that suddenly there's all these like biological productivity happening around these islands, and if anything, the flow interactions around these islands can sort of liken it to being an ecosystem generator. So, for example, when the currents, they hit the island, right? You can have upwelling processes, and then also just by the shape of the island as well, you can have vortex shedding that also, help to increase to promote a nutrient transport and heat transport around the island. You can also find that, for example, let's say if you have heavy runoff from the island, that also can result in very localized productivity in the surrounding waters. So it's basically the idea that these islands, they're able to support this high biological productivity, right? And one of the research that we're trying to do, is really to try and understand these processes, and you can try to resolve these processes through measurements and, of course, ocean modeling. But the thing is, where are most of the world's islands located? So every ocean definitely has every ocean basin has islands, okay, and most of the world's islands are scattered across the Earth's oceans, but their distribution is not uniform. So certain regions of the world actually have higher concentration of islands compared to others. The Pacific Ocean actually is home to the largest number of islands of any ocean on the Earth. All right, and some of the world's largest and most well-known island chains in this region are Hawaii, the Galapagos Islands, Fiji, Tahiti, Philippines, and they range, they have a huge variation in size from atolls to large land masses. The second place that has a lot of islands is also in the Indian Ocean. Okay, and for example, we know of the Maldives, the Seychelles, Sri Lanka. Sorry, excuse me. Apologies, I'm currently recovering, so a little bit phlegmy at the. All right, so about notable island chains in the Indian Ocean, they include Seychelles, Madagascar, Sri Lanka, the Andaman Nicobar Islands. We also have in the Caribbean a high concentration of islands too. And you have islands like the Bahamas, and all right, but also one place that which is a bit more personal to me since I'm from Singapore is also Southeast Asia, and it's also another region with a very substantial number of islands. For example, Indonesia is the world's largest island nation. It has over 17,000 islands. Then there's also Malaysia and Brunei and Thailand, which have their own concentration of islands as well. So when we think about where all these islands are, okay, with the Pacific having the highest, and then the other different ocean basins, the next question we should then ask, sorry, the next question that it leads to is, where are most of the global ocean observations then located? So this is actually taken from the Ocean Ops report card. Sorry, just give me a second. Sorry, apologies for that. So following on from what I mentioned about where are most of the global ocean observations recorded. So this is an example of where all the sea level tidal gauges are located in the world. All right, so far quite a high density. And then the next one that we have is where are long-term time series observations recorded. Okay, so all of this represents where they tend to be located. Then we have moored buoys. Sorry, excuse me. And we can see that, yes, this is where we can see there's quite an uneven distribution of observations around the global oceans now. And then, so this is for Argo floats, quite densely distributed. But we can also note that there's quite a gap in the Southeast Asian region, especially. Right, and around the Indonesian archipelago as well. And then we can look at where is the location for tsunami buoys, where they tend to be located. And also the data gets more sparse over time. And this is where we have a record of the historical transects from shipboard measurements. So just so you know, this is updated as of 2021. So I think there may be more, but this is just to give a general overview of how unevenly the global ocean observations tend to be distributed. So if we look at the databases for islands, it tends to be quite sparse considering where most of them are located. And in this case, just give me a second. For example, in South China Sea, so remember how earlier on I showed you that there was quite a scarcity of data available within the South China Sea. We saw that there was like hardly any data, especially like for the tsunami buoys or for there's a lack of tidal gauges as well. I mean, we have a few, but not a lot. Considering how dynamic this region is, and with the different tidal regimes that go on within here. In the South China Sea, some of the data that we tend to look at are, a lot of the altimetry, satellite, and drifter data, but even then, not a lot of information that we can gather So what are the implications of that, right? Because when we want to do regional modeling, we have to then think about what goes into a model. And a model is only as good as the data that we procure. So we always say that your model rubbish in, rubbish out. So if you don't have good data in, you're not going to have very good results coming out for your model too. And in a model, some of the things that we would input, right, it includes our forcing data, like our atmospheric forcing. That includes things like wind stress, short wave and long wave heat fluxes, freshwater fluxes, tidal data, right, temperature and salinity, and of course bathymetry. So when we think of islands, remember how I said that it is very constrained by the size and the land boundedness and the isolation and all. We're also thinking of it in terms of a completely different resolution that is available from the global and regional climate models that are currently out there. And, especially if we want to model island scale processes, then resolution definitely matters for every single model input. So this brings me to the next issue on islandness in climate data. So remember how in the previous slide I was saying that one of the model inputs that goes into like our forcing, so this is an example of the grid of ERA5. And this is where we would typically get wind data from. And this is my island, Singapore. And this is the general coastal model that we operate at. But if we just look at the island of Singapore under the overlaid with the ERA5 grid, we can see that this island by itself is only fitting into two squares, right? Two squares of the grid. The ERA5 currently is at like a quarter degree. So we have a lot of local scale processes like squalls or tropical storms that actually come from the island of Sumatra nearby, and it's impossible to capture any of those processes in the models, in the global model data that we want to use. So we can't really apply it directly. Similarly, if we look at another data source for atmospheric data, CFSV2, we find a similar issue that, yeah, we don't really, as a country, right, as an island, we don't really exceed more than 2 grid cells, and it's impossible to kind of resolve any of the microclimates that we were talking about earlier. Now, if we look at ocean models, for example, so this is now is overlaid with the Copernicus, the CMEM Copernicus environmental monitoring data grid. Even then, let's say if I wanted to get boundary conditions from Copernicus, it is also very cost. So it's the orange grid over here. And we face a similar issue with HICOM as well. So because of the coarseness of the data and the processes that we wish to resolve, there's definitely what we would say a scale mismatch going on. And this feeds on earlier to the issue of what I mentioned about microclimates and the complex topography of the islands, right? We have to account for the fact that islands are a very unique system, and if we have very coarse data into our models, we are not going to be able to resolve any of this. And even if we are to use, global projections, right, they are not exactly applicable directly for islands, because they are supposed like global climate models and regional climate models. They cover such a coarse resolution, and it's not it makes it very difficult for adaptation planning, especially for climate change. So earlier, this is what I mentioned about the Hawaiian archipelago, that because of its topographic complexity, we have, the interaction of the wind above land, but also the interaction with the currents. And then as the wind is interacting with the land and pushing water offshore, we also have upwelling processes that occur. So, this is actually a very good schematic of the convergence and divergence of the current flow around these islands, and simply due to the complexity of the island shape itself. So another thing, as I mentioned earlier, is that islands, because of their unique, both topography and bathymetry. So this is an example of in the South China Sea. So this along here represents the Indonesian archipelago, right? And we can see that, oh wow, like these are very, very complex bathymetry going on. And that also means that translates to a complexity of flow topography interactions. Then especially for our sub-mesoscale processes. So when I talk about sub-mesoscale here, I'm talking about anything less than 30 kilometer in the length scale. And one of the really interesting things is that if we cannot resolve the sub-mesoscale processes within this South China Sea region, there are a lot of processes that we cannot account for. For example, like heat transport, nutrient transport, or even general connectivity. And the impact of the sub-mesoscale actually has a lot of implications. So, for example, this is from one of my papers from my PhD, and we actually found that, so this over here represents a vorticity plot. So where there is high green color, it means there's a strong negative vorticity, and where there's red, there's high positive vorticity. Right? So vorticity in this case actually changes across different climate years. So this column here represents, the interaction of the islands and the vorticity, right, that happens at different depths. So when the currents interact with the Maldives, okay, the islands actually will cause some vortex shedding to happen, and this usually results in island wakes. And we can sort of see that let's say under a positive Indian Ocean dipole year versus a neutral Indian Ocean dipole year or a negative Indian Ocean dipole year, we actually see that the strength of the island shedding vortices changes with depth. So we can see that this is on the surface, right? But then we also can see it from a 3D point of view on how the strength of the vorticity changes in different years. And this is actually taken for pure Indian Ocean dipole years. All right, so when we think of the sub-mesoscale processes, we also have to think about how these processes will change under different climate modes, because if we are able to understand this, then we can also better investigate the processes that support the general productivity and hydrodynamic conditions around these islands. So one of the another things to sort of really emphasize the importance of resolving island scale processes. So this was an experiment that was done that, let's say, we remove the islands, right, of like the Maldives Islands. Okay, so we remove the islands at different depths, and the only scenario that may be applied to this is, for example, let's say sea level rise happens, okay, and the islands are like completely covered. What are the implications for that? So in this sensitivity test, it was actually found that so in this top panel here, this represents sea surface temperature, and this lower panel here represents eddy kinetic energy. So in this is the control experiment where we found that, okay, so this is the general flow during the southwest monsoon, okay, a snapshot of sea surface temperature. And then this lower panel is eddy kinetic energy. Now, when we remove the islands, when we remove the Maldives Islands, so let's say it's a scenario where, it's completely inundated, there's no more Maldives Islands, completely overflow, right? We actually found that there was a direct change impact on let's say, along the south coast of Sri Lanka. So typically around Sri Lanka during the southwest monsoon, we actually have a eddy called the Sri Lanka Dome. And when you remove the islands, we actually find that the intensity and the current flow along the southern coast, right, actually changes. And we can see that in terms of energetics, right, we can see that it's a lot weaker as well. And that's really because the presence of the islands there, right, they actually think about it in terms of when you have a sieve, right, and you're forcing water through a sieve, right, the jet flow through it is a lot faster. But let's say you remove that entire barricade, the flow then becomes weaker. So being able to understand these like island scale processes, and this was actually done with a regional model that was, that had a 3-kilometer resolution, we're able to understand that, yes, at this scale, right, this is what can impact on the surrounding islands in terms of heat, in terms of energetics, right, and current strength. We also find that, yeah, you can see that the cooler waters, right, the temperature also changes as well without the presence of the islands there. Now, if we look at it from a 3-dimensional point of view, so in this, following on from the earlier sensitivity experiment, we actually find that, oh yeah, at the southern coast of Sri Lanka, there's also another eddy that forms around here. So this is where the dark blue, the sea surface temperature, the dark blue color is. And if we look at it from a three-dimensional point of view, we can see that like when we see the particle and we follow its track, it's quite a coherent vortex, right? Quite a coherent eddy structure. And this is how it looks like in the vertical transect of it up against the Sri Lanka, the continental shelf. But if we remove the islands of the Maldives, if we remove all the islands here, we then see that the flow weakens to the point, and actually the downstream impact of this is that, we see that the eddy structure that was previously here with the Maldives no longer exists and becomes quite incoherent as a structure. And this also affects the intensity of the upwelling. So this over here is this, the cool water goes up onto the shelf, and then over here we find that it doesn't really quite happen the same way anymore. So being able to understand all these submesoscale processes at an island scale, it has a downstream impact on connectivity processes, and especially in the Southeast Asian region, where it's home to the Coral Triangle, right? All of these coral reefs and high biodiversity in the marine waters. So this is actually a snapshot from one of our particle tracking models, where we actually release particles from the known coral reef maps around Southeast Asia, and we actually tested it at different scales to see that under a coarser model resolution at like 10 kilometers versus a finer scale resolution of 500 meters, we actually found that there were differences in the reporting of the cumulative transport of these particles, of where these particles tend to end up. If anything, more often than not, we tend to have an overestimation. So if we are able to resolve submesoscale processes better for our regional models, we'll be able to actually reduce the uncertainty and understanding a lot of these connectivity processes. Yeah. So traditionally, when we think the current approach to regional models is that we would typically have a global model. We'll have a global ocean model, and the global ocean model would then provide boundaries to a regional ocean model. So it's a very nested approach. And the regional ocean model is, then provides boundaries to a local coastal model. Right. So this is a traditional downscaling method. Sorry, excuse me. Yeah. So there's right, and climate dynamical downscaling is actually the key to bridging the gap between, the limitations of having really cost scale global climate models, and yet also trying to answer the fine scale climate information that is needed for regional assessments and adaptation planning. Unfortunately, if we also look at this also requires high computational power. And if we look at the distribution of where major supercomputing centers are, most of the island nations do not really have that kind of resource, right? So that's also one of the challenges that's going on, that, we can say that, oh, yes, is the answer just to dynamically downscale everything, but what is the computational cost of it? And, I think one of the things that we also have to think about is that this traditional method of nesting, that also comes with its own measure of uncertainty, right? Because there are uncertainties in global climate models, there are uncertainties in regional climate models, right? So in a way, our uncertainty is being compounded through every time we do a nesting approach. There are several. So, for example, this is one of the approaches. This paper is that, we're trying to cover, like in Singapore, we're trying to downscale from a global climate model from 150 to 300 kilometers, then to a regional climate model to 12 kilometers, and then we try to get it down further to 2 kilometers. But even then, we can see, that is not really enough to resolve a lot of like the small scale coastal processes. Yeah. So, like I mentioned, there are several methods for dynamical downscaling. I'm not going to go through all of it, but one of the TDD is actually the traditional dynamical downscaling that I was talking about. Oops, sorry. which is, that we have the limited nested approach. Then the PGW actually represents what we call the global warming downscaling method, and it's actually used to project the climate response to increasing greenhouse gas concentrations. We also then have several mean and variance bias correction methods and the quantile correction. Then there's also the nested bias correction. And then we have a bias correction of multi-GCM ensemble and the GCM and RCM bias corrections. So like I mentioned earlier, each of them have their own advantages and their own limitations. And really, the traditional approach is always to use this one, but over time, people have developed other downscaling methods. And at this point in time, there is no, standardized approach to how we handle dynamical downscaling, especially for islands, right? It's about what works best, especially when we try to validate against our local observations. But then that's a bit of a catch-22 situation, right? Where first we don't have enough observations to validate against. So how do we also know that the method that we are choosing for dynamical downscaling is also appropriate? So that is actually one of the, even if you do want to validate your models, you are constrained by this data limitation as well. So another approach that we can think about in trying to resolve, this challenge in regional modeling is that we should also consider tapping onto alternative data sources, right? So instead of just relying on like, oh yes, we're stuck here, right? We're stuck by this limitation of cost resolution. We're stuck here by this limitation of, not having enough computational power, right? Like, what is another way that we can try to overcome this? Uncertainty exists continuously in the backdrop of all that we do. So at some point, right, we have to make up our mind that yes, we're going to live with this uncertainty, and we're going to try and make decisions, for at the local level, at the policy level, and taking into account this uncertainty. But one of the ways that we can try to, overcome this is by having more local stakeholder input. I think that especially in a lot of these countries, a lot of these island nations, there's a lot of indigenous knowledge that is yet to be fully tapped on, a lot of historical knowledge of the land and the islands around. And also to engage in more citizen science, right? We should engage more with, people like the fishermen, with, and local citizens, especially, there's, especially with the internet, anyone can really help to collect data on terms of like water quality or, right, like, phenomena that's happening at sea, and also sort of integrate that into a unified database. So we should try to move to hybridization between, modern and historical data to sort of reinforce each other, so that, that it's in a way complementary for both at the model level, but also from the ground up. So it's not having just a top-down approach, but also a ground-up approach in trying to resolve and solve these challenges for regional models, and especially for islands where these processes are so localized and so specialized. Yeah. So yeah, that's what I have for today on regional challenges. And so if anyone has any questions, feel free to ask.
Thanks a lot, Dr. Danielle. We have a few questions on YouTube Live, and I encourage all of you to drop in your questions in the chat box so that we'll be able to share it with Dr. Danielle and get replies. So I'll just ask the questions that I've got with me.
Yeah.
So TVS Uday Bhaskar asks, why are the Rama network not fully represented? What is the time period of the locations indicated?
So that one is actually the Rama moorings. They are definitely, I think I didn't show them on this one, but this one was under the goose observation. And yeah, I'm aware of the Rama network. I just didn't quite show it across. They're part of the time series, the Mod Boys observations. Yeah. For the Rama network, I couldn't. I'm actually not sure what is the latest one. When's the latest update though? Yeah.
So you wouldn't be knowing the time periods of the locations indicated?
No, to be honest, I'm not sure actually.
Okay,
Yeah.
okay. Also, Patabi Ramrao asks, tsunami buoys deployed by India in the Bay of Bengal and Arabian Sea are also not listed in the plot.
Yeah, so that's the thing. Like I got this from the Ocean Ops report card. That's why I did say that it's more of a representation, but I don't think it's been fully updated with a lot of the information from, for example, I know like iGoose, they are very active in the area, so I think some of it has not been updated there. But this is what I mean that again, like it seems that information tends not to be centralized. Yeah. But yes, I am aware that there are some of the tsunami buoys in there, but it just seems that, yeah, like for the Ocean Ops report card, it seems to have been missed out. It's not been fully updated.
Okay. Nimit Kumar asks, in the simulations, the island chain was entirely removed or just as submerged relief bathymetry?
Submerged, actually. So we actually submerged it at different depths to kind of see that, like if how much of it was covered by water, this is how it will alter the flow patterns.
Okay. We have few more questions.
Yeah.
Dr. Prasad SJ asks, hi Daniel, as you said about using a quarter-degree wind ocean forcing, will it resolve all the islands unstructured grid approach? Will it resolve all the islands? Unstructured grid approach can be used instead.
So I've actually tested it with an unstructured grid as well, but even then it didn't seem to resolve a lot of the processes. So it's a similar challenge there. Yeah, I've tested with both structured and unstructured, and it's not well resolved still. Yeah.
Okay. He asks one more question. Which downscaling method is better as per your research? Demonstrating using a case study will give us a clear insight.
Oh, so like I said, at this point in time, there's no real standardized approach. And it's also, but for now, in my own work, I still tend to use the traditional dynamical downscaling approach. Yeah.
Okay, thank you. Abhishek Chatterjee says, very interesting talk. In your particle experiments, you use different model resolution. So how much is the disagreement between the different resolution models?
We actually found that it was up to a 34% changes between the 10 kilometer and the 3 kilometer, 2 to 3 kilometer resolution in the terms of like the concentration of the particles per cell. Yeah.
Okay. So should we wait for some more questions or I mean, I don't want to hold you longer. I know you're sick. So thanks a lot, Dr. Daniel. This was such an interesting talk, and thanks for patiently answering all the questions.
No worries.
We look forward to more engaging talks in the future, maybe on a different subject and on a different topic. We can have another interesting popular science talk by you. So thanks a lot. Thank you from INCOI's team, and thanks from the organizers of the event. So, Nimit, do you want to share any closing remarks or we can wrap this here?
No, just thanks again on behalf of INCOIS, and this has been very nice. And thanks for the commitment. I mean, you're struggling with health, we understand, but you did not want to, postpone it again. So that's the dedication we truly appreciate. And thanks for a very interesting talk.
Yeah,
Bye-bye.
Thanks so much again for inviting me and for organizing this. And thanks so much to everyone online who attended this talk. I hope this gave some insight on the island challenges we have, and that as modelers, we also need to consider more aspects of like of complementary data and testing out. Have a more collaborative effort to centralize a lot of the information so that island countries can have access to it. Yeah, so thanks again, everyone. And so sorry again for the coughing.
No problem. Thanks a lot, Dr. Daniel. Thanks a lot to all the participants who joined us today. We'll meet you soon in another popular science talk, which will be more details will be shared on our social media. So keep following us on Twitter, Facebook, Insta, LinkedIn for more updates. Thank you.
Okay. Thanks, everyone. Bye.